Okay, so today we're going to look at related rates. And the first thing I have on my notes is review, implicit differentiation. So that's perfect, we just did that. Okay? So related rates. I am sure you'll be thrilled to know that today is entirely about word problems. Yes, but that's okay, because the interesting questions are word problems, right? Nobody walks up to you and says, hey, 2x squared equals 5. And he goes, oh, right? So here's some interesting questions. A tanker starts leaking oil at 4 gallons per second. How fast is the oil spreading? That's a reasonable question. We might like to know that. If production of a product increases at 5 items per week, how fast is the rate? What is the rate of increase in profit? We might want to know that too. If a boat can only be pulled ashore by a rope on a mechanical pulley that goes at 4 feet per second, how fast is the boat coming in? Because maybe the hurricane's coming in, you're trying to get that boat up, you've got this much time, right? So there's some reasonable questions that are interesting to ask that are all word problems, and we're going to translate those into calculus that we can actually solve those problems with. So the idea is in the name, related rates. We're going to have rates that we either know or want to know. And we can find the one we want to find based on what we know once we have related them, okay? So we are essentially going to be finding equations that relate rates. So related rates tells you what to do. So let's start. I think it's going to be easiest to actually just start with an example. Let's just do the tanker question. How about that? That's not on here, but we'll do it anyway. All right, so we have the tanker that's leaking oil at 4 gallons per second. That's probably actually a slow leak, right? I think when those tankers blow a hole, it's a lot faster than that. So the question is, how fast is the oil spreading? This seems like an easy question. It's going to involve some geometry. And I think you have a problem just like this on homework, so this is good for you. Okay, so this is, again, where I encourage you to use good problem-solving technique. And the first thing is to list what you're trying to find and what you know. And then the next step is going to be finding equations that relate them. And if you can draw a picture, do so. In this case, in a couple of different cases for the problems we'll be doing for related rates, pictures will help you. So what do we know? We're trying to find how fast is it spreading. I'm going to interpret that to mean, I'm assuming it's coming out in like a circle, and let's assume that we want to know how fast that radius is growing. So we want to find the rate of increase of radius. How are we going to write that in terms of math language? Because we want to very quickly get to math. What is the rate of increase of radius?
The derivative of, should we find the radius for?
Yes, derivative with respect to what? How fast?
4 gallons per second.
Time. We are looking to find actually dr dt. When we talk about rates, this is always, almost always with respect to time. All right, so this is a per time kind of thing. So we're going to be doing ddt all today. No ddx's. Today will be all ddt's because we're interested in rate of increase or decrease with respect to time. So we're going to call our radius, and we want to know how fast is it growing. Well, so what do we know? We know this thing. What is this? What do gallons measure? Volume, right? It's a volume, you have a volume of fluid. So what do we know? We know, and your units will help you here, we know that we have 4 gallons per second. That's volume per time. It's right there. So what do we know? We know that dV dt is 4. Okay? So again, everything's about time here because it's a rate with respect to time. And the units will help clue you into that. Okay, so what else do I need to know here then? I've got a volume coming out, and I'm expanding this circle. I need to somehow connect, and this is the important part. Everything that changes, you need to be able to connect. So you need to connect R and V. That's the first thing you need to do, is say, how are those related? We'll get to the rate part second. There are 2 steps, almost always 2 steps. The first step is relate the items that are changing. Not their rates, just their quantities. So how will I relate R and V? Well, what shape do I have? This puddle, right? It's a circle, but it's actually got a little bit of height to it. Will you agree that's true? Because it's like laying on top of the water. So this is actually more like a disc. Oh, I'm going to have a big old unit problem. Okay. I'm going to change gallons to a unit that will make it easier for us to do this. What unit is that? We're going to go with feet cubed. Is that also volume? A foot is length. Foot squared would be area, square feet. Cubic feet would be volume. So this is still volume. Okay, so we have this puddle forming on the top of the water. Everyone with me? Because it's floating, because it's oil. So how thick do we think that is? Let's go with the height of this oil slick. Let's go with, I don't know, 3 inches. Does that, I mean, I'm sort of pulling that out of the air, but does that seem plausible? I think that's plausible. Okay, so how will I connect V and R based on this? Now this is something that you guys probably learned way back when and probably don't remember. Don't worry about that. I will give that to you on a test. Okay, so this is a disc. Does everyone agree that's a disc? Or a really squat cylinder? It's kind of like a tuna can, only really, really squat. So the volume of this is pi r squared h. I just know that the volume for a cylinder is pi r squared h. Okay, I know you guys probably, that may be far enough back that you don't have that off the top of your head. That's okay, don't worry about that. Okay, so, but now look what I have. Is h changing? No, I'm saying let h, it's always going to be a 3-inch tall puddle. So h I know. Now look at this. I have now related V and R. That's the whole first step. So the whole first step is figure out the rate you want to know, the rate you have, and relate not the rates but the quantities. So now I have that. Okay. Let's just go ahead and plug in h because we know what it is. H is 3 inches. An important thing when you're doing problems with units is that your units need to match. If I'm in feet here, I would really like for this to be in feet also. So how many feet is 3 inches?
0.25.
0.25? A quarter of a foot, so 0.25. So we're going to plug that in here. So finally, this is the equation we're going to have to work with. No, I already had the h. 1/3 pi r squared. That's what connects the two. Does that make sense? This is not the problem I meant to start with, but this is sort of a more real-life one. Okay, so that's great. We've related V and R. Awesome. What are we trying to find? So I've got R and V. What is left out of this? D dt. That tells me what I have to do next. So I've got the R and the V connected. Now I need to do the d dt part. That's really just implicit differentiation, right? Didn't we just do that? So we're going to d dt this whole thing. I'm going to write it as a separate step. You don't have to. Will any of the derivatives we're about to do be straight basics? No, none of the variables match, right? This t doesn't match any of these. So we know that all of them are going to have an inside. Nothing is straight basic. So let's start with this one. What's the derivative of v with respect to t? You just have to write d dt, like there's nothing else to write. The derivative of v with respect to t is dv dt. One quarter in pi, those just carry through and just multiplying, so let's just write those down. Now, what's the derivative of r squared with respect to t? These don't match, So it's a chain rule situation. So I'm going to say the derivative of r squared is 2r times the derivative of the inside with respect to t, so dr dt. So far, so good?
dr dt or d dt?
Well, ddt is here, but when I get over here and I'm taking the derivative of r squared, it would be 2r times the derivative of its inside. So yeah, they're going to be, so each one of these, every time you take the derivative with respect to time of a variable, you're going to get a d something dt. So you're going to have lots of ddt's floating all through class. All right, so now let's look. What am I trying to find? This one. Do I have dv dt? Yes. Do I have, yes, 1/4, I have pi. Do I have r? I don't have r. And that's one of the things that's, yes, you have a question?
Yeah, I'm still trying to figure out like why you just didn't like cancel out the 1/4 of the pi. 'Cause, like I was thinking just like they should be constants, right? And
They
it's
are.
just-
So, but they are multiplied through. So it's kind of like if I say 4x squared, it's 4 times 2x is my answer, 8x. So if I had 4 pi x squared, that's still just a number. So it's still just 4 pi times the 2x. So pi is a number, it multiplies through, so it's not a product. And the reason, so you could treat it as a product rule, but if you did that, the derivative of pi over 4 would be 0 and you'd lose your whole second term anyway. So anytime you're multiplied by a constant, you can treat it like a product rule. If you do it correctly, you'll get the right answer, but otherwise it just carries through. It's just pi is weird because it's pi and it's not a number. I mean, it is a number, but it's not a number. So this illustrates one of the problems we have with related rates, and that's this. I will have a rate I'm looking for, I will have a rate I know, but often I also require a little bit more information. And so what you'll often see in a problem setup is how fast is the oil spreading when the radius is, I don't know, 100 feet. So there's going to be an extra bit of information that gets put in there. And so it's going to be important to tease those apart when we get to the plugging in stage. The important piece is to concentrate first on your rates. Anytime you say, I know a rate, I'm looking for a rate, you're thinking rates, you're thinking, I got to relate the rates, bless you. You're thinking related rates. So the first thing you focus on is the rates. Figure out the rates you're trying to find, connect the quantities, do the derivative with respect to time, and then here, now you start plugging in pieces. So this is where that r equals 100 will come in. Because if the radius is small versus large, it's going to be expanding at a different rate. I mean, r will be. All right, so now we're ready to plug in. So dv dt, 4, equals 1/4 pi 2 times 100 times the thing we're trying to find. In my engineering class, I always tell them you have to solve for this variable first. I'm not making you guys do that, but generally that's good practice. So if you don't have, if it's easy enough to do, I recommend that, but don't feel like you have to. All right, so now I can just solve. So here I get 4 equals 200 divided by 4 is 50 pi. So dr dt is 4 over 50 pi. Let's actually get a number on that. So this is one where you are going to, this assignment you're going to need a calculator because you'll end up with a lot like this. So I got 0.0255. Word problem, word answer. So what I need to at least put units on this. So I'm saying that my radius is increasing. It's positive, so it's increasing, that we expect. Increasing at what? 0.0255
feet squared.
Well, it's a radius, so just feet per second. And how do I know that? I know I need 2 units, one for r and one for t. So if you label things correctly, again, problem solving, if you've labeled things correctly, it helps sort of propel you through the problem. Okay. So let's just recap in this. We're going to do a lot lot more, and then I'll have you do some on your own. Okay, so this is an interesting question. This is something we may want to know. The first thing you do when you're reading a word problem is when you start seeing rates with respect to time. I know this rate, I'm looking for that rate. When you start seeing multiple rates with respect to time, that suggests related rates. So that says, write down the rate you want to find, write down the rate that you know, and there may be more than one rate you know, that's fine. Connect the quantities, the R and the V. Anything that can change, you need to relate. This height, I'm saying, is not changing. So I can just go ahead and plug that in. If it's not changing, you can plug it in. But if it's changing, you have to leave it as a variable. So connect the variables that are changing, and then take the derivative with respect to time. Now I have my rates. So now I just start plugging in everything. I plug in everything, and I get my answer. Yes?
Are we going to be given the equation on every problem?
Yes.
Okay.
Yes. I believe that's true. And if not, the only ones that you might need, let me write up a list of what you might need. All right, so over here, here's a list of what you might need. Guaranteed you will need Pythagorean theorem. That's a popular one here. So you're going to need that for right triangles. You're going to need some volume equations. So volume of a cube is just x cubed, whatever the side is cubed. Volume of a sphere. Anyone remember that one?
So something with base times height.
No, close, no. 4/3 pi r cubed. That makes sense because r cubed is going to give us the volume. It makes sense that it's got a cube in it. Cylinder, that's the one we just did. Pi r squared h. I remember that one because I think it's an area of a circle, pi r squared, and now I stack it up h high. So that's how I remember that one. Area of a circle, pi r squared. Area of a square, x squared. Area of a rectangle. A lot of times we just write length times width. What else do we need? Oh, circumference, last one. Anyone remember the circumference of a circle?
2 pi r.
Yes. 2 pi r. So I think those are all the ones you're going to need. Pythagorean theorem you should know. On a test, I would give you whatever you needed to know for this. I might just write them up on the board. So if you're looking for volume, you have a set. Area, you have a set, and circumference. All right, so let's do some more. Okay. Let's do this one. Let's do this one. All right, let's do the ladder. The ladder is the infamous one. So you have a 15-foot ladder resting against a wall. The top of the ladder is 9 feet up on the wall. I know I'm not writing it very formally. The ladder starts slipping. We know we can't slip up, we're going to be slipping down. So the question is, so slipping at 1 foot per second. So the question is, how fast is, so if the ladder's coming down, what's the bottom doing? If the top's coming down, what's the bottom doing? Sliding out, right? So the question is, how fast is the bottom of the ladder sliding. Okay, so let's read through this problem again, because the point of word problems I know that most people have trouble with is, how do I know what kind of a problem it is? That's a reasonable question. And when you get out in the real world, that's how everything is. How do you know what tools you bring to bear on a project? You need to analyze the project and see what it's about. So here we have a ladder. We know where it is presently, and we know that it starts slipping down the wall. So we know it's coming down this way and it's kicking out that way. So the question is, we know this rate, how fast is that happening? So anytime I start seeing rates, I know one rate, I'm looking for another rate, that suggests to me related rates. So if you want to, go ahead and write down related rates. That will help kind of remind you what you're trying to do. So this is a related rates problem. So the first thing you need to write down is the rate you're trying to find and everything you know. And everything you know is going to include rates plus other information. It's going to include some geometry, what kind of a shape you have, anything that you can use to connect the quantities. So what am I trying to find? I'm really thinking a picture is going to help immediately, because I need to start labeling variables. So let's just go ahead and draw a picture. So here's my wall, and here's my ladder. So let's label some sides. You want to just do A, B, C? Does everyone see this is this is a right triangle? So let's just do A, B, C. Okay, so we've got our picture. Let's come back and start writing some things. What do we know? We know we're trying to find how fast the bottom of the ladder is moving. So B represents the distance out the bottom of the ladder is. So what would I write for how fast it's moving? What math language how would I describe that? It's not just B, right? B is the distance. I'm not trying to find B. I'm trying to find how fast it's sliding. So it's going to be, yeah, dB dt. So that's what I'm trying to find. How fast is that bottom moving? What do I know? I know how fast the top is moving, right? So what variable will I give that? How fast the top is moving? Yeah, dA dt, exactly. A is the distance, and it's changing, so it's a dA dt. And I know dA dt is what? 1 foot per second, and I need to be careful with related rates about signs. Is this distance getting bigger or smaller? Smaller, so the rate is actually negative then. Yeah, so I need to be careful with that. So -1, and you can certainly put on feet per second. Don't know anything else. But right here, A, the ladder's not 9 feet tall, but it's up on the wall. The top is 9 feet in the air. So I know that at the point of interest, remember, because the rates are going to be different depending on where you are. So once I'm at A equals 9, that's the point of interest. These are going to relate, and this is the point of interest. What else do I know?
C equals 15.
C equals 15, because I know it's a 15-foot ladder. Okay, so now, so I've listed everything, I've got a good picture. So now I need to think, I need to relate these. Just those quantities. Everything, so I'm only relating the quantities that change. So is there anything on this picture that does not change? C. C is always 15. That means I can use it. If it does not change, use the number now first. So how do I connect? So the point is now I'm trying to connect A and B. So how do I connect A and B? A squared plus B squared equals 15 squared. You won't always know, this won't always be the case. It may be that you know B and you don't know the hypotenuse. So it won't always work out with the variables on one side. It might, but it might not. So just don't force that. Let the picture kind of guide you. Okay, so, yes?
A squared be 9 squared.
No, because it's changing. So, and this is the difficult part about related rates. I want to know what dA dt is when it's 9 feet. The top is 9 feet in the air. If the top is 6 feet in the air, it's going to have a different rate. If the top is 1 foot in the air, it's going to have a different rate. So that's where I really concentrate first on the rates. I mean, that's a great question because that's where people tend to get hung up. They put this in too soon. Okay, so the thing that you want to do is figure out the rates that you want to find and want to know, and you must relate those variables as variables. This gets plugged in later, you'll see that in a second. Okay, so I've related, so this is equation number 1. I have related the quantities. Now I need to relate the rates. So how do I relate the rates? What do I need to do? If you're not sure, look right here. There's the rest. I need to ddt the whole thing. Okay, so I'm going to ddt that thing. And I know that 15 squared is 225. Okay. Are any of these going to be straight basics? No, because the variables do not match. Okay, so we're always going to have a dA dt, dB dt. I'm going to have ddt's on everything. So what's the derivative of a squared with respect to time? First I get the 2a, and then dA dt. So the 2a takes care of the outside. This is the outside, 2. This is the inside, a. Okay, so 2a takes care of the outside. dA dt takes care of the inside. I do the same thing with b. So you go ahead and write down what that is. Write down the derivative of b squared with respect to time. Everybody get that? 2b dB dt?
Mm-hmm.
Derivative of 225?
0.
0. Okay, so now let's look across. Good catch. Let's look across and see what we have and what we need to find. So we are trying to find dB dt. We have dA dt. We have A, our point of interest. We're missing B. Anybody see what we can do? We need a B value. Say again? Well, that won't help me because I'm trying to find dB dt. So I've got to find somewhere else. I need to look somewhere else where I can get a B value.
Would you just plug in A?
Where?
A squared?
Where? Here?
The second?
Here?
Yeah.
Wait, since we're going to A and C.
Up here, up here,
Yeah.
yes, up here. So not the DDT part, but up here. So the thing that you need to know is if you need an extra variable, remember this is your point of interest. I want to know what's happening when A is 9. But when A is 9, do I know what B is? Yeah, just come right back up here. So that's why I number both of these equations, because you may need to come back and use this first equation to get more fixed values. So how do I find B? B up here. So I'm going to say 9 squared plus B squared is 15 squared. I designed it on purpose so B is 12. For those of you that remember 3, 4, 5 triangles, this is one. Okay, so now I know B also. So now I know everything. Right? All right, so let's start plugging in. 2 times A, which is 9, times dA dt, which is -1, plus 2 times B, which is 12, times dB dt. So can I solve for dB dt? Yeah, so -18 plus 24. So altogether dB dt is going to be 18 on the other side, divided by 24, so 0.75 what?
Feet per second.
Feet per second. Because this thing is sliding out, and again, it's right here. If you're not sure, it's right here. What are the units on B? Everything's measured in feet, so feet. What are the units of time? Come back to your original problem, seconds. So dB dt, the reason I don't write B prime is because dB dt tells me more information. So do I expect that it's positive? This is a step, this is the last step. You need to make sure that it makes sense to you. If you got a negative number here, that would be a problem because the ladder can't be coming down this way and squeezing in this way, right? So it's one of those things that your answer should make general sense. The sign at least should make sense. Also, if you got, like 75,000 feet per second, you might think, it's a little extreme. So yeah, so make sure to look, did I do this correctly, 18 divided by